So I would like to welcome all the students, dear teachers, and it's a pleasure to welcome all of you in this session through Carrios. In the next 1 hour, I will make you to dive in some of the essential topics in chemistry. Primarily, it has been tailored for class 12 students. However, I have tried to keep the concept as such that even the students of class 9, 10th, and 11th will be able to enrich themselves, and I hope it will be valuable for them also. So I'll be sharing which topics I'll be taking because I've just got about an hour, and hope the session will be insightful for all of you. Already you would have prepared lots of theory part, so I'll try to keep it interactive, project based, and experiential to the extent possible. Right. And I've tried to gather some videos for all of you so that the topics can be taught in an interesting manner. Uh, so, with your permission, can I start?
Yes, sir, absolutely. Please go ahead. Just before you start, I would like to request Anamika ma'am to sort of formally introduce Carrios and all of the sessions that we have to all of the children over here. So over to you, Anamika ma'am.
Thank you. Very good afternoon to everyone, to all the students and the teachers who are present in this session. So, as you all know, Carrios is an online platform where we are trying to initiate interest in the students about STEAM, because sometimes it's very difficult to reach out to very big professors or to have sessions like this that we are going to have to do, and have a lot number of students included in one particular session, which is really fruitful for everyone. So conducting all this in an online mode, sometimes it becomes very easy. And this idea actually popped up in the COVID times when we were really struggling with, to have all these kind of sessions and really initiate science and STEAM in our students. So from then we have started this initiative, and it's really going well. And now we have different student anchors who are taking care of this, to take this forward, this Carrios. And we have different initiatives from Carrios team. We have magazines and the special sessions that we have started now. These we are calling as master classes, because as we know, we are going to have board exams for grade 10 and 12 very soon. So to help our board students, we thought this is a very good initiative to have our very good teachers, our own teachers across the campuses who will take sessions on specific topics which are really, which the students struggle with. So here today we are starting with the first session, and Mayank sir, a lot of thanks to you for accepting this and taking the initiative to have this session with the students. And Mayank sir has already done this kind of session before, and it was really very good. And the students have actually they gained a lot of interest in chemistry and a lot of insight into how to prepare for the board exams, which is very important. Sometimes we know the knowledge, but we don't know how to prepare for board exams. And we will be having a lot more sessions like this in the future. So we will let you know about all those sessions, and I hope it will be helpful for all of you. So Mayank sir, thank you so much. So can we start then for today?
Yeah, thank you, Namika ma'am. Thanks so much. Thanks for such a humble talk about me. And only one thing what I'll try my level best is to make the time which is going to be devoted by the student, it should be fruitful for them. One request, to the extent possible, I'll try the session should be very interactive. You can put in your queries in the chat box, and at times when required, you can also unmute yourself and come online. So basically, the topics that I'm taking today, I would like to share with you all. So I'm going to touch three different parts of chemistry in near about 55 minutes that I'm having in my hand. So the topics that I'm taking in. The first one is colligative properties. Now, we all know that, I hope it's visible and it's clear.
Yes, sir, it's visible.
Right. So the first topic that I'll be taking that is from the chapter solution of physical chemistry in class 12. And one of the topic which was given by students while I was asking which topic should I take during the session. So one of the topic which was shared by student to explain was ionic equilibrium. Now, ionic equilibrium is basically the topic of class 11, but again, it helps us in solving the numericals of class 12 also in the same chapter solution. And after these two topics, I'll be also going towards reaction in organic chemistry and mechanics. Now, at times you'll be feeling, oh my God, this much. But again, I've said to you that I'll try to keep it interactive. I'll try to keep the things as much humoristic as possible. So again, a request to all the children, it would be great if you can switch on your cameras. It's better every time if the teacher can see their students who are in front of them. So I also feel good and will feel confident along with you all. So, right? So can we move ahead? So let's start from the first property, that is colligative property. Before going to typical colligative property of class 12, I would again like to engage with class 9th and 10th students also. So the first thing that I would like to start from is, I hope all of you know the boiling point of water. So I hope you can unmute yourself and can tell me what's the boiling point of water. 100 degrees. 100 degrees Celsius. That's perfectly all right, and everyone knows it. Very fine. Now, the second question that I would like to ask you, what do you understand by boiling point? Like, if we go under typical definition, what is the definition for boiling point of any liquid, say for the case? So again, if I'm going to request any one student to please unmute and specifically of class 9th or 10th, if they can give me the definition of what's the meaning of boiling point of a liquid, I'll really be thankful to you.
So when the vapor pressure of the liquid state becomes equal to the vapor pressure of the vapor state, then it's called, then it's the boiling point.
Okay, so if I'm correct, Nidhi, probably you are from class 11 or 12. You are from 9th, not from 9th or 10th. So I have
Sorry,
said
sir.
it needs to be answered by any student of class 9th or 10th.
Sorry, sir.
It's perfectly all right. The reason why I came to know you are from class 11 and 12 was from the kind of definition you have given, because a 9th and student does not usually give this kind of definition. Because that's why I'm saying that I want the definition from a student of class 9th or 10th. So any student of class 9th.
Sir, when vapors, when the water particles, for example, or any liquid state, are heated to such amount that the intermolecular spaces of the particle increases and the kinetic energy increases of the particle, then the liquid is converted into gaseous state.
Very fine. So basically the definition that a 9th or 10th class student knows is that when a liquid gets converted into its vapor state, then this temperature at which the liquid starts to get converted into vapor state, this temperature is known as the boiling point of the liquid. Now, coming up to what is the interrelationship between vapor pressure and what is the how it is interrelated with the atmospheric pressure. So first thing that we are going to understand is what is the meaning of vapor pressure, first of all. So vapor pressure is the pressure exerted by the vapor of any substance. Again, I'm repeating, vapor pressure is the pressure exerted by the vapors of any substance. Now, this substance can be in the liquid phase also, it can be in solid phase also. And of course, gaseous themselves are gases, so they, of course, exert pressure. Now, the question is, liquid do convert into vapor state, and we say that its vapor can exert pressure. Now, in the case of solid state of matter, do solid state of matter also exert vapor pressure? What do you feel? Now again, this is a question which is out of the box. Do solid state objects also exert vapor pressure? What do you feel? Now, my question, I hope is clear to you all. I have asked that do solid state objects also exert vapor pressure?
Everyone, I would like to reiterate that the purpose of the session is to have a lot of interaction. So don't hesitate. Just feel free to unmute and give your responses. We're all here to learn.
Okay,
Anyone?
I'm flipping it. You all said that water boils at 100 degrees Celsius. Can water boil at about 70 degrees Celsius? Yes, no.
Yes, sir, it can boil. Yes, sir. Yes, sir.
It can boil. That's very great. So you know the answer. Yes, it can boil below 100 degrees Celsius. It can boil even at 70 degrees Celsius. It can boil at about 80 degrees Celsius also. So I have got an experiment for you. Here I am having a water bath. In the water bath, as you can see, I'm holding it. So the temperature of the water is near about 70 degrees Celsius. It's just lukewarm. So I'm very comfortably able to hold it up. Now what I'm going to do is, I've got a syringe here, and inside it, I'm going to take water as I am pulling back the piston. So here you can see the water is inside the piston. Further, what I'm going to do, I'm going to close the opening knob with help of my finger. And now just observe what's going to happen. I'm going to pull the piston backwards. And can you all observe something? What's happening? So please, if you can share your observation.
Bubbles are forming. The water is boiling.
Yeah, very fine. The water is boiling here. And the water is boiling, though the temperature is just about 70 degrees Celsius. So can you, and the reason behind it is very simple. I hope you all know about it also. The reason behind it is we reduce the external pressure. I reduce the external pressure as I pulled back the piston. And as the external pressure reduced, the vapor pressure of the water became equal to the external pressure and it started boiling. So the important thing here is, what's boiling point? The boiling point is the temperature at which the vapor pressure of the liquid becomes equal to the external pressure. Now we all know very well that we are surrounded by air. We are covered by air, which is known as atmosphere. And typically the pressure exerted all around us, that we have given the unit of 1 atmospheric pressure. So under normal conditions, whenever the pressure of a liquid becomes equal to 1 atmospheric pressure, the vapor pressure of the liquid becomes equal to 1 atmospheric pressure, the bulk of the liquid starts to get converted into its vapor state, and we say that the liquid has started to boil. And in normal conditions, the liquid has a boiling point of 100 degrees Celsius. Very fine. And here itself, again, I'm reiterating the typical definition for class 11th and 12th students for the boiling point is, when the vapor pressure of the liquid becomes equal to the external pressure, in general atmospheric pressure, the temperature is known as the boiling point of the liquid. Now, I'm returning back. Do solids also exert vapor pressure? That was one my question. So what do you feel? Liquids, of course, very conveniently, they get converted into vapor state. Do solids also exert vapor pressure? That's my question. So whatever might be the...
Maybe yes.
Very good. Maybe yes. So the answer is yes. Now we all are very familiar with the concept of sublimation. I hope you all know. Like if a naphthalene ball is kept somewhere, it gets converted into its gaseous state, right? So the property of sublimation itself is an example that solids can directly get converted into gaseous state. At the same time, even I'm going to talk about iron, the solid iron, if I'm going to say, at the minuscule level, at a very minuscule level, the particles of iron, they come in the gaseous state, but they are extremely negligible, and we presume that no vapor pressure is being exerted by the solid iron. But again, at the minuscule level, yes, even a solid object like iron also exerts vapor pressure. So that's certainly surprising. But again, this vapor pressure is extremely less. So in general, we say no solid object like iron do not exert vapor pressure. But again, at a very minuscule level, they do. And it requires lots of temperature to make the vapor pressure of a solid like iron to become equal to the atmospheric pressure, which is near about much more than 1500 degrees Celsius. Okay, now here we've discussed about vapor pressure, we discussed about boiling point. Coming up back now, as we have to return back to our property, colligative property of class 12. Now, if I'm going to take water, so I'm having water here, right? And in this water, you all know very well, the boiling point is 100 degrees Celsius. You all know it very well. Now, in this water, I am going to add little amount of salt, that is sodium chloride. So, let's see. Okay, so here I'm having water in which sodium chloride has been added. So we are going to do an experiment here. First of all, we'll see water, which is normal. We'll see its boiling point, and the boiling point will be, everyone knows it's 100 degrees Celsius. And then we'll observe what is going to happen if we are going to add salt in it. Very quickly, we'll complete this experiment because we have to take a few more topics also. So, can I have boiling water? Boiling. And thermometer. Boiling water, please. So here I am having water. Hope you can see the reading of the thermometer.
Not clearly, sir.
Not clearly. I'm trying to focus it up.
So we can't read the reading, but we can clearly see
It's
like
50 degrees Celsius. I think.
It is above 50 now. It's
Yeah.
much above 50.
Yeah, 52 or something. But it's just around 50.
yes, sir, it's visible. We can see.
So this is what you have to observe. I want boiling water again, I'm saying to you. So is it visible?
Yeah, it's clearly visible.
Now, can you tell me the temperature? What is it at present?
52 degrees Celsius.
Very fine. Now, I've just set for boiling water because this, of course, is again lukewarm water. Okay, so before I'm going to get boiling water here, let's come to return back to the topic. So the boiling point of normal water is 100 degrees Celsius. If we are going to add salt to it, the salt molecules, when they dissolve, then how they are going to affect the vapor pressure of the liquid? Of course, they are going to occupy some of the spaces at the surface, and thus the vapor pressure of the solution which has been formed, that will be less in comparison to, if you can complete my sentence, the vapor pressure of the new solution formed, that will be less in comparison to the vapor pressure of pure water. Am I clear to my children?
Yes, sir.
Yeah, so normal condition, the vapor pressure of the solution which has been formed by dissolving salt in water, that has become less in comparison to water. So now this solution which has been formed by adding salt in water, it will boil at higher temperature or lower temperature according to you. It would be great if I can get the answer. I hope again everyone can participate.
Higher temperature, maybe.
It will boil at higher temperature. That's great. So now, as the surface molecules have been occupied by sodium chloride, non-volatile solute, the vapor pressure of the solution which has been formed, it will be less in comparison to pure water. And that is why I want something here that keeps on boiling. I want burner here.
Excuse me, Mayank sir.
Yeah. Yes, ma'am.
I just, I'm not able to see clearly, and my connection is bad. But at the same, meeting is there, sir. It's just a suggestion. You can put some paper behind the grid so that they can read some white paper so that children can
Okay.
read the phenomenon.
Right.
And,
Clear.
yeah, yeah. My connection is slightly weak. I hope I'm clear. I'm not able, or I don't know whether I'm audible or not properly.
Perfect. We'll do it. We'll do it. We'll do it. Okay, so as the vapor pressure of the solution which has been formed by adding sodium chloride is less in comparison to pure water, so the boiling point of the liquid solution which has been formed will be more in comparison to pure water. And this property of elevation of boiling point due to reason of addition of a non-volatile solute in water is itself a colligative property. Why is it called a colligative property? Reason being, the boiling point elevation completely depends upon the amount of, the number of solute particles which have been added in the solvent. Right? Now I'm going to show you this experimentally. Okay, should I turn it? It's here. You can even bring the camera. Okay, so I'm just doing something for you. So here we go. If you can just hold it here. Yeah. Himanshu sir, yes. You can put it here. So is it visible, all the children?
Yes, sir.
Yeah. So here, what is it? It's a water bath. And I just want you all, yeah, just put it here. And I want a paper or a copy if you can bring it. So that what will happen, children will be able to observe the mercury level rising.
Could you lower your camera just a little bit so that we can see?
I am doing it. Let me just arrange the flame and then I'm doing it.
Yes, sir. Thank you.
Yeah. Just wait a minute. If it will just focus. Just focus. Yeah. You can. I am just wait. You can start. You can know what नहीं करना. It's working.
Mayank sir, your camera is invisible.
Okay, wait a minute. Just 1 minute.
Yes,
So
sir.
I need to switch it off.
Yes, Sonia.
In the meantime, I would request everyone to please turn on their cameras because the essence of the session is that it's interactive.
Children, am I visible?
Yes, sir.
Now, is the mercury level visible?
Yes, sir.
Yes, sir.
So what's the temperature now?
Sir, you're not able to see that. You can only see the red mercury.
Sir,
I
we
think
are not
it's
able to.
52 or something.
We can't see the reading properly, sir.
Okay, that I'll share with you. Don't worry.
पीछे में
Yeah.
सर अगर आप थर्मोमीटर के पीछे थिंक पेपर रख देने से दिखेगा आई थिंक सो But you can tell the reading, like.
Okay, so the reading now at present is 60 degrees Celsius. Is it visible?
Yes, sir, we can see the level rising.
So we have reached up to 80 degrees Celsius now. $90. Anything visible? The level is rising. We have reached up to
93.
93. That's great. We have reached up to 95. I hope you are able to observe. Children, is it visible?
Yes, sir.
So we are about to reach at 100. Now, in the case of normal water, what do you feel? Will this mercury level cross the 100 mark or not?
No, sir.
No. That's the answer. That's absolutely correct. Now we are going to do something. Let it reach up to 100 mark. Let the mercury level touch 100. Now my question to you is, can you see the mercury level touching 100 point?
About to. Not means clear, but about to. We are able to see.
Okay, now you can see the water is boiling and the mercury level is at 100 degrees Celsius. Now I'm going to add sodium chloride in water. Somewhere, are you able to see the level 100 or not?
Yes, sir.
Sir.
Is it visible?
Yes, sir.
It's visible and it's more than 100 now, I think.
Okay, 100, maybe that would be due to reason of some impurity in water. And now I'm going to add sodium chloride and just observe how the mercury level rises very sharply after it. So here we are adding sodium chloride. That's enough, yeah. And now let us see what happens to the mercury level. So any observation regarding the mercury level?
So it's rising like 105 only.
It has reached up to near about 104 degrees Celsius at present. Right. So I'm coming back to the experiment now and to the class after this part gets over. So what has happened here? The sodium chloride, which has been dissolved in water, that is occupying the space of the surface. Due to reason of this, the vapor pressure of this liquid has become less in comparison to pure water. And that's why the boiling point of this solution is more in comparison to pure water. Is this clear to all the children or not?
Yes.
Yeah. So returning back to the theory part now. Yeah. Just right. Let's return back to the classroom. So just so as I shared with you, this elevation in boiling point was due to the reason of addition of non-volatile solute. The elevation in boiling point completely depends upon the solute which has been added. And this property, which depends upon the number of solute particles, it is independent of its nature, is known as colligative property. Right? Now, let's see how the formula is written for it. So I am coming to the board back. Children, am I audible?
Yes.
Yes. So earlier, the temperature of water, saponification was 100 degrees Celsius, and I'm writing it as boiling point temperature initial, that is for the pure water, that is written as TB naught. Now, the new temperature, it is much more, that I'm writing as TB. Now, this temperature is for the water plus salt solution, and this was for pure water. Now, can you just tell me whether TB naught is more or TB is more? Of course, the boiling point of the pure water is less and the boiling point of the solution is more. So what we can write TB, that is the boiling point of the solution, minus boiling point of the pure water. This will be equal to delta TB, and this itself is known as the elevation in boiling point, which is a colligative property. Elevation in boiling point is directly proportional to the concentration of the solute particle, and this has been identified experimentally as molality. Molality is the concentration that we use for identification of the concentration of the solute particles. So that's why we did elevation in boiling point is directly proportional to the molality, that is the concentration of the solute particle. Further, I'm going to bring a proportionality constant. I have written elevation in boiling point is equal to Kb to m. Here Kb is again a proportionality constant, which is known as molar elevation constant, which depends upon what kind of solvent that we are using. So it depends upon the nature of the solvent. So Kb value for different solvent is different, and whenever numerical is given for solution, the value is Kb is given to you. The molality part will be given to you, and you have to identify the elevation in boiling point. Right. Further, if you want to open it up also, I hope much of the students of class 12th and 11th would be knowing molality is equal to the number of moles of solute dissolved per kilogram of solvent. So if I'm going to open it up, delta TB is equal to KB into, now M I'm writing is number of moles of solute, that is N2, upon mass of solvent, that is W1. Now for the reason it is in kilogram, so I'm written further here, upon 1000. Further, N2 can also be opened up, that can be reduced. So I hope it's visible to all of you. This is the final equation that we use for solving of the numericals. Now, the variables will be given and anyone can be asked you in the examination. The numericals related to colligative properties are extremely simple. If you know this formula, if you know how it has been derived, I hope you are not going to have any kind of problem in solving the numericals related to elevation in boiling point. Now, I hope the second topic that I'm going to take in relation to it will be much more interesting. There were some technical glitches, which I hope will be a part of online class. But next part, which I'm going to take, I hope there will be no glitch whatsoever. Now, returning back very quickly to the freezing point of water, and I hope everyone knows what's the freezing point of water. That is 0 degrees Celsius. Now, again, how can we determine the freeze? How can we interrelate the freezing point of water with vapor pressure and the freezing temperature? So here goes the definition. The temperature at which the vapor pressure of a liquid comes in equilibrium with the vapor pressure of the solid, the temperature is known as freezing point. Now, if I'm going to say that at 0 degrees Celsius, what happens? At 0 degrees Celsius, the vapor pressure of the water becomes equal to the vapor pressure of the liquid, right? If I'm going to add salt in water, what will happen to the vapor pressure of the salt solution? Will it be more or less? Again, the answer is the vapor pressure will become less. And that's why the vapor pressure of the solid solution will also become less. And that is why you need to reduce the temperature even more to reach up to the solid proportion of that respective solution. And this property is known as depression in freezing point. Now, I would just like to show you this experiment. Now, here I'm having ice in a bucket. And I hope this experiment goes on quickly. And I'll be using a camera now. Now, can you see the temperature here? No, not visible.
Yes, sir, we can see the bar, but not exactly read the reading.
Now, can you read it?
Yes, now we can read it. It's close to 0.
Very fine. It's 0 degrees Celsius. Now, what I'm going to do quickly, I hope you all have observed it very fine. I'm going to add salt in water and let us see what happens to the temperature level. So I have added salt here. And again, I would like to show you the reading of the thermometer. I hope it will be legible. Just keep it stable. I will be able to concentrate there. Yeah. No, just put it there. Please. Put it here. I'll do it. Uh, yeah, can you all see it, children?
Yes, it's less than 0.
Very fine, very fine. This is what I wanted to explain you. So here we can see the freezing point of this solution became less in comparison to water. And this technique is used for melting of ice in the hill areas where the temperature is near about 0 minus 1 degree Celsius. Once the salt has been sprinkled on the snow, which is there on the road, what happens? The freezing point depresses, and due to reason of which, what happens? The due to freezing point depression at 0 degree Celsius or even at minus 1 degree Celsius, the ice is not able to be in the solid state because it is not pure water. It has reached in the solution state and it starts to melt. So here again, if I'm going to relate it, just like elevation in boiling point, as I've written this formula, now I'm going to write delta Tf, that is depression freezing point. This will be equal to Kf. What is Kf? This is again a proportionality constant, it depends on the nature of the solvent. Multiplied by concentration of the solute, which is going to be represented by molality. And then if I'm going to open molality once again, I can write here mass of solute for molar mass, which again is equal to the number of moles upon mass of solvent in kilogram. So here we go on with the second colligative property, which is depression in freezing point. So two things I hope are clear to all of you. One was elevation in boiling point, which happened due to reason of the depression of the vapor pressure of the pure liquid. And second, we studied about the depression in freezing point, which again happened due to reason of the decrease in the vapor pressure when we added a non-volatile solute in the solution. I hope these two things are absolutely clear to you. The formula which has been explained to you, I hope it's clear. And again, just keeping in mind that what is this formula all about, I hope no numerical whatsoever is going to create a problem for you. So am I clear regarding these two topics, first of all, my children?
Yes, sir.
Right. Thank you very much. Moving up to the next part very quickly. Now we are coming up to the ionic equilibrium part. What is the meaning of ionic equilibrium? So before starting, just one thing, you all have studied very well about various chemical reactions. What is the meaning of equilibrium? Equilibrium state is when reactant part is also present and the product part is also present simultaneously. So that is the equilibrium between the product and the reactants. My question to you is, what do you feel? Much of the reactions go for completion or much of the reaction remains under equilibrium state? What do you feel?
Sir, that the reactions remain in equilibrium.
That's the correct answer also. In fact, you'll be surprised to know that 90% of the reactions remain in equilibrium state because industrially also it is beneficial for the company itself because whenever they want, they can once again convert the reactants into products. And say for the case if the products are not required, then they can convert the product back to the reactants. So they are not going to be in any kind of financial loss regarding the commodity which are being used. It is something like if you're in a sweetmeat shop, if you're owner of a sweet shop, you prepared sweets and say for the case by the evening the sweets were not able to be completely sold away, then what can be done due to reason of equilibrium reaction? You can convert the sweet once again back to the raw products, that is ground flour, sugar. The next day you can then again prepare the fresh sweets. So that is why industrially for the chemical reaction, it's beneficial if the reaction goes under equilibrium. For the completion of the reaction, once it takes place, then once again we cannot reach up to the reactant state. So that is why 90% of the reaction are created in such a manner so that they can reach up to the equilibrium. Now, before going to the ionic equilibrium part, I would just like to explain to you one very normal topic. I hope 11th class students know it very well, but it will be very beneficial for 9th and 10th class students. That is electrolyte. So first thing, what's the meaning of electrolytes? So electrolytes are the substances which, when dissolved in water, they dissociate into respective ions. So in this manner, if I'm going to ask sugar, I hope everyone knows the formula of sugar, that is C12H22O11, or if I'm going to say glucose, that is C6H12O6. So does glucose dissociates into ions in water? What do you feel? Yes or no? No answer.
No, sir. It does not dissociate.
It is not dissociate. Yes, because it's a molecule. It's a molecule. Right? So sugar does not dissociate in water, but there are certain, if we talk about salt, if we talk about acid, if we talk about base, they dissociate in water and they furnish ions. And due to the reason of this, what happens? They are able to conduct electricity. So let's see a very interesting experiment. Again, it has been devised for you. Here I'm having a conductivity tester for you. And what is this conductivity tester? I have arranged the buzzer. There is a LED. And once I'm completing the circuit, let us see what happens. And then further, I will be showing you some experiments related to electrolytes. And then we'll go to ionic equilibrium. So once I've completed the circuit, you all can see that the LED is glowing and you can hear the buzzer. Right? Now what I'm going to do is, I'm going to take pure water. So here I'm having distilled water. Now you all know distilled water does not consist of any kind of dissolved salts or impurities. So, and also water, I would like to ask, it's a good conductor of electricity or a poor conductor of electricity? No answer. But the answer is, it's a poor conductor of electricity. Reason being, there are no ions whatsoever in a distilled water. Right? So, right. So now what I'm going to do, I'm putting the wire of this conductivity tester inside the water, inside the distilled water, and let us observe what happens. So you can see the LED is not glowing, no buzzer, and we can assume that there are no ions whatsoever present inside the distilled water. Now what I'm going to take tap water. Now tap water is usually potable, and it consists of some amount of dissolved salts in it. So what we can assume here, some amount of dissolved ions are present in the tap water, and let us see what happens. So any observation?
So there's the faint glow of the light.
Excellent, excellent. There is a faint glow of light. Very good. But you can see the buzzer is not working, correct?
Yes, sir.
Yes. Electricity.
Very fine. So it means in the potable water, in the tap water, there are some dissolved ions which are essential for our body, but they are in extremely less quantity. Okay, very fine. Now what I'm going to take glucose solution. Here is a glucose solution, and glucose solution, again, it is in tap water itself. And let us see, hopefully you know the answer, what's going to happen. So again, you can see a very faint color glow of the LED, right?
Yes, sir.
Yes, sir.
Right, again, there are no dissolved ion. That's great. Thanks. And now I'm going towards acetic acid. Now, let us see what happens in the case of acetic acid. Now, acetic acid, of course, there would be some ions present in water. And let us see whether the LED glows in a very intensified manner, how the buzzer makes the sound. Let us see. Yeah, so what's your observation?
The LED is glowing, but the buzzer is not glowing.
Excellent. The LED is glowing, but the buzzer is not working. It means acetic acid is a weak acid or a strong acid, according to you.
Weak acid.
Because it furnishes very less number of ions. And
Yes.
yeah, great. So it furnishes very less number of ions. And now I'm going to take the next one. I'm going to take dilute hydrochloric acid now. So what's your observation?
The buzzer is working
Great.
at
Great. So it means hydrochloric acid completely dissociates in water to give hydronium ions and chloride ion. Right. One thing more I have done, I have taken a salt. The salt is aluminum sulfate. It could also have been sodium chloride. I've dissolved in water. It means ions are present in water. And I hope you know the answer as the ions are present. So result is but obvious. In presence of ion, the conduction is taken.
Yes.
Very fine. Now, coming up very quickly to ionic equilibrium part. So, what happens in the case of ionic equilibrium? I would like to take the example of acetic acid. Now, is it visible to all of you children?
Yes, sir.
Now, acetic acid is a weak acid, and there is an equilibrium between the dissociated part, that is acetate ion, and hydrogen ion, which the acetic acid furnishes on dissociation. Right? Now, obviously, the concentration of this is very much less in comparison to the amount of acetic acid that we have taken. Also, we study about dissociation constant of the acid. Dissociation constant of acid tells us about what is the strength of acid. With the help of dissociation constant, we can determine the strength of the acid. Now, the Ka value of acetic acid is of the order 10 raised to the power minus 6. Right. So this is the dissociation constant order for acetic acid. It means obviously it is very, very, very less. It means we are going to get very extremely less amount of ions of acetate and H positive due to reason of dissociation of acetic acid. And let's take the reverse case. Let's take the case of HCl. In case of HCl, you can see I have just put in a forward headed arrow. I am written H positive, I am written Cl negative, and I am written the value of Ka, which is near about 10 raised to the power 7. It means HCl undergoes complete dissociation. And that is why the value of K is 10 raised to the power 7, which gives information that complete dissociation is taking place. The value of K for acetic acid is 10 raised to the power minus 6, which gives information that extremely less amount of dissociation is taking place of acetic acid. First of all, I hope till here is everything clear to all of you.
Yes, sir.
Yeah. So both of these are electrolytes. Which one is a strong electrolyte? That is HCl, because it furnishes a large amount of ions, due to reason of which the conduction of the liquid solution is also very high. The other one is acetic acid, which furnishes very less amount of ions, and that is why the conduction is also very less. Now, what I want to explain with the help of this. Now, in 11th class, the biggest problem that the students face in the ionic equilibrium chapter is the numerical. So, how the numericals are to be solved in this case. So, I'd just like to share my screen for this part, or even I can share here if it's visible. So, let's go to desktop and here. So, is the screen visible to you all children or not?
Sir, could it be zoomed in a bit more?
I'm sharing my screen with you. Don't worry. Wait.
Alright.
Yeah. Um, Children, I'm not able to share my screen. I'm just trying it once again.
Okay, sir. No worries.
I hope I'm not having the permission to share the screen.
So the permission is given.
It's given.
Right.
Select this one. Okay. Is my screen visible?
Yes. Yes, sir.
Yeah. Is it visible?
Yes, sir.
Yeah. Is it visible?
Yes, sir.
Yeah. Can you just read the problem? Is it visible?
Yes, sir. It is.
Yes, sir.
So the question goes on, the dissociation constant of acetic acid is 1.75 to 10 raised power minus 5. So you can see the dissociation constant is extremely less at 25 degrees Celsius. Further, if 0.10 m acetic acid is dissolved in water, what will be the concentration of acetic acid, acetate ion, and H positive ion at equilibrium? So first of all, can you understand the question or not?
Yes, sir.
So here they are, the equilibrium constant value has been given and the equilibrium concentration of acetic acid, acetate ion, and H positive ion has been asked. We have written the initial concentration. At equilibrium, what will happen? Some amount of acetic acid will dissociate to give acetate ion. The same amount of concentration is subtracted from 0.10, that is the initial concentration. Then we put it in the formula of equilibrium constant. That is concentration of acetate ion, concentration of H positive ion, and undissociated acetic acid. The values have been put in. And finally, we can see the value of X has been calculated, which ultimately will give us the value of the concentration of acetate ion and H positive ion. Now this is the numerical which, if the concept is clear, all the numericals which are there in equilibrium, they follow near about the same concept. So this is what I've tried to cater in the case of ionic equilibrium, because basically the problem that the student faces in ionic equilibrium is the numerical part, which I've tried to cater here. Now, coming up to the last portion of this session, that is organic chemistry reaction mechanism. So I have got some very interesting videos for all of you, and a request, though we are running out of time, but I'd like to take 5 minutes more of yours, and I hope it will be fruitful for you. So I have got something very special. Again, I am sharing the screen, and first let's have a look of the video, which is again going to be related to the ionic, which is going to be related to the reaction mechanism. And you'll be surprised how it is related to the reaction mechanism. So again, can I share my screen, or is this visible to all of you? Is the screen visible here?
Sir, the screen is visible.
Screen is visible. Then I would like to show it to you here itself. So here we go. Children, is the screen visible, or should I need to share my screen?
Sir, it's very clearly visible.
Okay. So I would like to ask you, what is probably your observation on this screen?
Sir, a flight is taking off from the airport runway.
Very fine. And at the same time, you can see another flight is also landing.
Right.
So Just observe this video. One of the flight is taking off. At the same time, another flight is landing here. Right?
Yes, sir.
Right. And let's assume the runway here is a hydrocarbon chain, which is a substrate. Now, the leaving aeroplane, let's assume it is a nucleophile, the leaving nucleophile, and aeroplane which is coming and landing here, that is the attacking nucleophile, which is going to come and attach here with the hydrocarbon chain. Is it making sense?
Yes, sir.
Now, what's the meaning of nucleophile? Of course, I hope 11 12th class students will be very much familiar with it. The nucleophile are the charged species, or either they are having a negatively charged, they are negatively charged ions, or either they are having a lone pair electron, and they are attracted towards a positively charged species because they are in hunger of nucleus. They are having negative charge, so they want to donate it somewhere. So here the runway, which is a substrate, which is a hydrocarbon part. Here we can see an attacking nucleophile is the aeroplane which is landing. At the same time, another aeroplane is the nucleophile which is taking off. Right? So now when this is happening, can you just tell me that which out of these two aeroplanes, which I'm going to say nucleophile now onwards in organic chemistry, is going to be stronger? This nucleophile which is taking off, this is stronger, which has been removed, or this nucleophile which is landing, which is attaching with the substrate, this is a stronger nucleophile. What do you feel?
The one that is attaching.
Very good. The one which is attaching, that is a stronger nucleophile. So whenever there is a stronger nucleophile attacks a hydrocarbon chain, then the weaker nucleophile has to leave. And this itself is known as nucleophilic substitution reaction. Here what is happening? One of the nucleophile is being removed, another nucleophile is getting attached, and this is known as nucleophilic substitution reaction. Now, this kind of nucleophilic substitution reaction, what is happening here? The reaction depends upon the leaving nucleophile also, and also it depends upon the nucleophile which is attacking. So it depends upon two molecules simultaneously, and that is why this kind of nucleophilic substitution reaction is known as nucleophilic substitution bimolecular reaction. I'm repeating, nucleophilic substitution bimolecular reaction. Am I clear? Does it make sense or not?
Yes, sir.
Right. Now, here few things I hope you all remember. You would have studied it. I would just like to wrap it quickly. This happens usually in the case of primary alkyl halide, because in case of primary alkyl halide, the nucleophile can attack very conveniently. And that's why one of the nucleophile attacks and the other nucleophile gets replaced. Right. Now, I would like to show you one more video and let's see what happens in that case. Okay, so what's your observation here? As I shared with you, this is the runway, and runway we are assuming that's a substrate, and the aeroplane is coming to land here. So how many aeroplanes, that is nucleophiles, can you see here? One or two?
Just one.
Just one, that's great. It means the rate of the reaction is just going to depend upon what? It is going to depend upon the runway, that is the substrate. If it's vacant, then from which direction the aeroplane is coming, it does not matters at all. And that is why the rate of the reaction just depends upon the substrate. And that's why in this case, when the nucleophilic substitution reaction is taking place, one of the nucleophile has already been removed. That is, one of the aeroplane has already left away from the runway. It is already gone. And then when the runway is empty, then another nucleophile, that is the aeroplane, is coming to land. So So in this case, as the rate of the reaction depends only upon the concentration of runaway, that is substrate. That is why it is known as nucleophilic substitution unimolecular reaction. Nucleophilic substitution unimolecular reaction. So again, I was running out of time, so few of the things which I wanted to share here, I am skipping those all part. But majorly what I wanted to explain to you, whenever you're studying reaction mechanism, try to interrelate the things in this way. So in this manner, the reaction mechanism becomes equal for you, becomes easy for you. So that's it from my side. I hope I was able to justify nucleophilic substitution reaction. I was able to justify the electrolytes, strong and weak, and ionic equilibrium. And further, the first topic that I took, which took quite a long time, that was colligative property. So here I rest this class at present, children. Yeah.
Thank you so much, Mayank sir. Anamika ma'am, could you please culminate the session so that all of us can leave with our takeaways?
Yeah, thanks a lot, Mayank sir. The way you have taken the session, I think the children have really gained a lot of insight into the 3 difficult topics that you have tried to explain today. And especially the demonstration part, like even I was totally stuck to the computer, to my laptop, and I was looking at the demonstration, that it really helps to understand the concept so easily. And I think visual impacts, they create such effect, they will stay with you forever. So I think they have really gained a lot from today's session, and now this difficult topics will be easier for them to deal with. And thank you so much. Thank you for giving this time and taking this session.
Thank you so much, Ramika ma'am. Thanks.
Yeah.
Yeah,
and I hope everyone has taken down notes. And if you have any doubts, even if you have not interacted within the session, but I would request you in our next sessions that will come up. It's better to interact. Then it's easier. That's why we are having these sessions, because we rarely get such good teachers to interact with. So when you're getting one-to-one interaction, it's better you ask your doubts. So even if you have any doubts after the session, you can just write to us. We'll try to solve it out. Yes, sir?
Yeah. So again, thanks for all the children. Thanks for your time. And I hope I was able to justify the topics that I taken. Thanks very much, children.
Thank you.